cascaded inference based on softmax confidence. And the research question, the global one, is how to reduce the computational effort in deep neural networks. So the motivation for this question is that deep neural networks are practically everywhere in every AI system today. And we really want smaller and faster deep learning models because those are just some examples. We have situations like in drones or in autonomous vehicles where we are either limited by energy budget or by low power supply. And we might be also looking for real-time constraints, such as in the autonomous vehicles, where we need a quick response of the system to the situation. So we need a faster model. We also can talk about green computing in the sense of data centers, in the context of data centers, where the data centers are very energy hungry, and if we can reduce the computational effort there, we're gonna also have a gain in energy bill. There is a lot of previous work that deals with reducing the computational effort for training or inference, and some of it deals with devising new hardware accelerators that use lower precision or better memory architecture. But of course, there is even more work being done on the algorithmic aspect of model compression for faster inference, or distributed training for faster training. And of course, I can mention the neural architecture search, which is a huge line of work that deals with developing an automatic developing of efficient architecture. So neural architecture search can be also guided by energy constraints, for example. But in this work, I want to focus on inference. And in order to make the inference efficient, I'm gonna make an adaptive computational effort. I'm gonna adapt it to the hardness of the input. And as a running example, I'm gonna use image classification tasks. So the principle of making the computational effort proportional to the hardness of the input can be restated as easy images should be faster to classify. And if you look at the right image, this one is quite easier to classify as a dog, rather than this one, which the left one, which also contains features of a moose or of a clown. And I would expect that a model should compute the classification of the B image much faster. But this is not the case in almost all the deep neural networks because they do not distinguish between easy and hard inputs. They just have one input, one output, and the same computational effort for each input. And this leads me to the attempt to define hardness of the input. This is quite hard. So to make this task a bit more tractable, I will try to measure the hardness of the input with respect to a given model at hand. And for example, let's take the cascaded structure of a neural network, where you have several layers, and let's say that you can output a result after every layer, for example. So if I have this structure of a model, then I can try to define the hardness of input X as the minimum number of layers needed to be invoked until a correct classification of the input X. Okay, so this will be the hardness of input X with respect to cascade. And this leads me to a practical problem. So we need to know the ground truth answer of what is the class of X in order to define its hardness. So yeah, it's a bit not practical at the test time. So all we can do is to actually try to estimate the decision of whether we should continue the computation or to stop the computation. And anyway, this also leads me to the idea that if I compute several layers and then I decide that I need to go further, I want to actually build up on the previous computation and to continue from the place that I stopped in order to reuse the computation. Because if I'm not using a cascaded architecture, if I'm using just a bag of experts, then if expert number one won't return me a correct or a confident answer, I will need to invoke a second expert and to begin the computation from scratch. So there will be no reuse of computation. So I really want to stick to the cascaded architecture. And there are several works that do something similar, that they use a cascaded architecture and they estimate the confidence after several layers, but they do not provide a methodology that will allow me as a user to decide when do I want to exit the computation. They deal with sophisticated thresholding approaches. Some of them actually have this branching architecture that does not exhibit a good reuse of computation. So we really want to address these drawbacks in our implementation. So now I'm gonna show you our technique. So you can imagine that you have this deep neural network which has feature extraction at its core, at its main computational effort core, and it has a classifier, a small classifier at the end, a bunch of fully connected layers. So we introduce additional, those one in red, those additional classifiers, and each classifier should be able to classify the input and to provide the confidence. And we want to use as a confidence the already existing maximum of the softmax score that is being generated at every classifier that is being used in deep neural networks. So this addition is computationally small, and yeah, so this is the general structure. So how do we do the inference? We allow the user to input the input X, and also to provide epsilon, the tolerable degradation in the accuracy that we want to be able to tolerate. We can set it as 0 if we do not want to tolerate any loss in the accuracy, but from this epsilon, our methodology will derive automatically the thresholds for all the individual intermediate classifiers, and then the input will begin traveling through the computational graph. First, it will be classified by the first classifier. If the threshold of the confidence is met, then we quit the computation and look how much computation we saved. But if not, we just go one more stage, again comparing against the threshold. So delta is the output confidence of classifier, and delta hat is the threshold that we set for this classifier. If again we are not satisfied with the confidence of this classifier, then we go all the way until the end. And at this unfortunate situation, you may argue that I can just throw my whole technique into a trash can because I just invoked redundant computation and I just made it worse. But I assume that this is not going to be the case in most of the inputs. Most of the inputs are going to be easy, and I hope that this the first classifier and the second one will be the ones that will be the last ones. So how do I train this cascade? So I want first to train the deep path, the core of this cascade without the additional classifiers. Then I freeze it, I fix the parameters, and I optimize only the redundant, the intermediate, you name it, there are many names for them, the intermediate classifiers. And this allows me to actually force them to adapt to the feature extraction taking place along the deep path of this cascade. And in my experimentation, when I try to jointly optimize all three of them, these ones actually cause the degradation in the top performance achievable by this model. And as a side goal, I would not prefer my cascaded model to have a lower accuracy than the original one. Okay. Last thing that I want to tell you about our approach is this automatic methodology for threshold setting. Because as I told you, the user provides this epsilon, this single knob that it can twist, and we derive the individual thresholds for each one of the classifiers along the way. So for each classifier, I'm going to do the following procedure. And I will do it only once after the classifier is trained. Imagine that I'm lining up all the inputs of the validation set on this line. I'm running all of them through the classifier. I'm obtaining the confidences, and I also know whether the classification ended up correct or not. So I have those correctness flags. I then sort them with ascending confidence. This confidence, I remind you, it was just measured from the classifier. It was emitted by the classifier. And now I'm just preparing this small table. I'm just, imagine that I'm going from right to left, and for every prefix from right to left, I'm writing a tuple of a confidence and the accuracy. For example, for confidence of 0.9, all those 5 inputs satisfy this threshold. So and we have only 1 mistake out of 5. So the accuracy prime, I call it accuracy prime, would be 80% for a threshold of 0.9. So once I computed this table for each one of the classifiers, I keep these tables accessible. And when the user in the inference time gonna introduce some epsilon, I'm just gonna pick up those tables and look up the threshold, the minimum threshold that satisfies this degradation of 1 minus epsilon. And that's it. And this sets the threshold for each classifier. So again, I'm stressing this thing that accuracy prime for every classifier is computed only once. This table is computed only once, and it's very easy to look up in this table. So the advantages of our approach are that we do not require a specialized confidence estimator training. We just use the already existing softmax. Every classifier has a softmax operator in it. Sharing computation takes place, only the small amount of computation in the classifier is not reused, and this is good. And we allow a dynamic control in the sense that the user can change the epsilon even from one input to another, and it will only require small lookup in the table to set up the thresholds. Another advantage is that you can take a pre-trained deep neural network and just add those intermediate classifiers and fine-tune them, and that's it. And you've got a cascaded inference framework. And actually, that's what I did. I took a pre-trained ResNet 50 that was pre-trained on ImageNet. Somebody spent like 2 weeks to train it, and then I spent 15 hours or something, and that's it. And I got myself a flexible model that can accommodate different accuracy to computation trade-offs. And if you're bothered with the fact that we never compute input after input, but rather we use a batched execution, so I can introduce buffers in between those components of the cascade. So all the discarded inputs that were not that did not satisfy a threshold can be gathered in this buffer until it's full, and then it will be processed by the next stage. This, of course, increases a little bit the latency, but this allows you to use partitioning to partition this cascade among several machines, for example. And as a last example, I also show you that the very popular ResNet architecture, which looks like this with 3 distinct residual modules, each of which containing several convolutional layers, can be turned into a cascade by introducing those intermediate classifiers. And that's what I did. And this is one of the models that I used in my experimentation. So let's look at the results. So the results are gonna be just they will look like this, like plots of x-axis being the computational effort, just in number of multiply accumulate operations, and the y-axis is going to be the accuracy measured across the test or validation set. When you use a non-cascaded, not what we present in our work, not cascaded model, then it can be represented on this plot as one point, that because for every input it will spend these 4 billion multiple accumulate operators, and it will yield the same accuracy on average. But if you introduce our approach, then you get this curve along which you can steer by increasing, you go to the left by increasing the epsilon, and we would be really happy to see this plateau, which actually exhibits this cutting away of the redundant fat of the neural network, because it was just trained for this worst hardness scenario. And when I slightly increase the epsilon, so more and more inputs starting to be inferred in the initial classifiers along the cascade, and you're starting to save computational effort on average. So on average, you will get much less computational effort. So here's a result on ImageNet data set on top 1 and top 5 tests. So we here I write down one of the sweet spots along this curve where we save 17% of accuracy, of computation, and we pay 1.3% in accuracy. One work did something similar to what we did, minus the dynamic control, and they do not show a good enough performance, because this plot is higher is better and left is better, so you want a really long line here. Other results that we achieved on CFAR and SVHN datasets show from somewhere from 34 to 54% in computation reduction. And again, we're paying for it roughly 1.2, 1.4% in accuracy degradation. There is also a bunch of ablation studies that we performed. Maybe I will touch one of them slightly. Okay, the being of softmax being as a confidence estimator is questionable, because if you are not calibrating it, then the confidence to accuracy curve is not going to be one-to-one. It's not going to be this identity function, but it can be easily achieved if you use a calibration approach, as described by the paper from 2017. You can look it up. It's called on calibration of the softmax. So if we calibrate the softmax before we use our approach, then this epsilon that we propose to set for the user to set is actually going to be really correlated with the degradation in the accuracy that the model is going to achieve. So to summarize, we proposed an architecture that allows an efficient inference in feed-forward deep neural network. Practically, we show the computational saving for a small accuracy reduction. We benefit from a dynamic control, which does not require retraining your model when you want to change this trade-off of computation to the accuracy. And you do it using one knob, this epsilon, and that's it. And we also talked about several other advantages, such as the usage of a pre-trained network and the scalability and the natural partitioning of the cascade among the machines.